We learned in a previous class about the stages of a statistical inquiry. And the first stage, of course, is to state your statistical question. The second stage is to design your experiment or design your study and collect the data. And then, of course, we have to analyze the data, and one of those phases, or one of the aspects of analyzing the data, is to explore the data. And so this video is going to talk about the different ways that we might explore the data using graphical and statistical summaries. So the first part is we're going to think about how we might describe the distribution of a categorical variable. And so categorical variables are those that have no quantitative meaning. So we might have numerical data, but those numbers don't really exist on a meaningful scale. So things like zip codes, things like social security numbers, stuff like that. Or it could also just be true categories like states, your major, or hair color. So the distribution of a categorical variable lists the categories, so those would be the different zip codes, the different majors, and gives either the count or the percent or proportion of individuals who fall in each of those categories. So in this case, we have the region, we have the number of attacks, so this would be shark attacks, and we have the percent of attacks. And so in Florida, in this given year, or in this time range, there were 271 shark attacks. In Australia, there were 141. In Hawaii, 52. South Africa, 47. In all other regions that were measured, there were 301, for a total of 812. So we could find the percentage of attacks in each of these regions by taking the total number of attacks in that region, dividing by the total number of attacks across all regions. So for Florida, for example, Florida's percent would be the number of attacks in Florida divided by the total. And that would just be 271 divided by 812, and that's 0.334. And of course, when we make that a percent, that's 33.4%. We can do that for Australia, and that would be 141 over 812. We did that for Hawaii. And so how would we find this for South Africa? For South Africa, that's going to be 47 over 812. And 47 over 812 is going to give us 5.8%, or the proportion of 0.058. For all other regions that are not specifically listed here, we would find the percent by doing 301 divided by 812, and that gives us 37.1%, which of course is 0.371. Now if we wanted to find the total percentage, the total should equal 100% because there is no more than 100%. And so of course we would do that by the same method as before, 812 divided by 812, and that just equals 1, or 100%. So our total should always equal everything, or 100%. Now if we wanted to represent this frequency table graphically, we could do that with a bar chart, which is represented on the right. Bar charts are preferred to things like pie charts because they are an easier, more visual way of getting the relative frequencies of each group to the other. So for example, we can see that Florida, if we're plotting the percent of attacks, has about twice as many of attacks as Australia. If we had done this in a bar chart, getting that twice as many is not, in a pie chart, seeing that Florida is twice as many, or roughly twice as many as Australia, is not as easy to discern. Similarly, we can see that Hawaii and South Africa have about the same amount of attacks proportionally as each other. And about maybe a third as many of attacks as Australia. Overall, we can see that all other regions combined have more attacks than any of these specifically named regions because this bar is the tallest. We can see that Florida is about twice as tall as Australia. And so that's how we'd read the ball chart. The labels and scales are very important. So we always label our axes. When we describe the distribution of a quantitative variable, we're going to do something besides just looking at the relative heights. We have to be sure to mention the shape, the center, the spread, and if there are any, the presence of any outliers. If we're going to describe the shape, there are four different things that we might look for. So for example, we might see if there is symmetry in the shape. And a symmetric distribution may look like this. And what we're really looking for is this line symmetry. If I were to fold the distribution in half, is the left side about the same as the right side? And we often see this with people's heights. A right skewed distribution is going to have a long right tail. So this longer right tail, if I'm looking at this plot, this is going to be why I have this right skewed. So long right tail. An example of a right skewed distribution might be something like hours spent watching television. Most of us spend our time down here around maybe 2-3 hours a day, but there are some people who spend many more hours than that. But there aren't a lot of people who do that, but they are pulling that distribution, that right tail of the distribution, up. A left skewed distribution is the opposite of a right skewed distribution. It has a long left tail and that's where it gets its name. We would see a skewed left distribution if we're thinking about the scores on an easy test. If we have an easy test, most people are going to do very well on it. Most people might get something around a 99, a 95, 99, 100. Some people aren't going to do as well, but most people are going to knock that ball right out of the park. But some people are going to do maybe 90s, 80s, 85s, right? So, but the bulk of the scores are going to be up here in the high A's. Now, the thing that the three distributions I've drawn here have in common is that there is one hump, one mode. So these are all unimodal distributions. You can imagine other distributions that would still be skewed right, skewed left, or symmetric, but have more than one mode. So for example, if I come over here, I could have a symmetric distribution that has two modes. So this is bimodal, but still symmetric. We're still thinking about if I draw a line down the middle, if I fold it in half, do those two sides match? We could think about bimodal, but right skewed. So that might be something like this. So I still have that long right tail, but if I fold it in half, those two sides, the left side and the right side, don't match. And I could also have a bimodal and left skewed distribution. Now those right skewed and left skewed distributions with multiple modes, we might say they often come from maybe like mixture distributions. So how they arise, we're not going to worry about the common examples of them, but they can in fact happen. And so that's why we're not going to just talk about whether a distribution is symmetric or skewed. We also have to look at the modality. So an example of a bimodal distribution would be the eruption times, times between eruptions of Old Faithful, the geyser at Yellowstone. Sometimes the times between eruptions are very short, but sometimes there's a very long gap. And so the distribution between those times is kind of clumped between those really short time periods and those really long time periods. When we have a quantitative variable, it's not enough just to talk about the shape, we also have to talk about the center. So we often talk about the sample mean. So the sample mean is the arithmetic average. So we take our sum of all observations in our sample and we divide by the number of observations in the sample. And so that's just going to be x1 plus x2 plus xn all over n, the number of observations. You do this all the time when you're finding the average of your homeworks or your test average for a given class. So how does the sample mean, how do the sample median and mode relate to each other when we have different shapes of our distributions? If we have a skewed left distribution, the mean is going to be less than the median, is going to be less than the mode. So it's skewed left, the mean is less than the median. So the mean is going to be drawn towards that extreme long tail. If we have a symmetric distribution, the mean is going to be equal to the median. They'll both be right in the middle. The mean is not going to be pulled in either of those directions. If we have a skewed right distribution, the mean will be greater than the median. And all this is to say is that these extreme values in the long tails pull the mean toward them. So the extreme values in this long right tail for a right skewed distribution pull the mean toward it, and extreme values in this long left tail pull the mean in that direction. So we've talked about how we can assess measures of shape, talk about shape, we can talk about measures of center, and finally we need to talk about measures of spread. So we're going to think about the sample standard deviation in this class. The sample standard deviation is the typical difference between sample observations and the sample mean. So really it's saying how far can I expect an observation to be from the sample mean on average. This is much easier to interpret than a variance. But the variance is easier to calculate. The sample variance is this squared thing. I don't have to take a square root, but it's not as easy to interpret because it ends up being, of course, in these squared units. So it is an easier formula, but it's not as easy to interpret. So we're going to use the standard deviation as our measure of spread, the sample mean as our measure of center, and we're going to talk about shape as in terms of both the modality, so how many humps in a histogram, as well as the skewness. So is it symmetric, or is it skewed right or skewed left? So let's think about spread here. I've got 4 histograms, A, B, C, and D, which show the distributions of test scores in 4 different classes. They're all plotted on the same scale, so if you look very carefully, we can see that they go from 1 to 5 on all 4 of these histograms. Which distribution has the largest standard deviation and which has the smallest? So if you want to pause this video for a second and kind of think about this, I'll give you the answer when you turn me back on. Distribution A has the largest standard deviation. We can tell because if we remember, the standard deviation tells us the typical difference between sample observations and the mean. So all of these are symmetric distributions. I can draw a line down the middle and I can see that if I fold it in half, the distribution is symmetric. So when I think about it that way, I can see that for distribution A, most of the observations are really far away from mean. In distribution C, all the observations are pretty evenly distributed around the mean. In sample D, all of the observations are exactly equal to the mean, they're all 3. And for distribution B, the observations are mostly equal to the mean, and then they slowly taper away. So when we're thinking about the typical difference, The biggest difference between the observations and the mean come from distribution A. So A has the largest standard deviation. Distribution D has the smallest standard deviation. In fact, the standard deviation here is 0 because there is no variability. All of the observations equals 3. With no variability, there is no standard deviation. The last thing we're going to do in this section is to identify the type of graph in the graphs below, whether there are explanatory and response variables, and then if there are both types of variables, which variable on the plot is in which role. If there are both types of variables, which is the explanatory, which is the response, whether they are categorical and quantitative, and how you describe these data using the concepts we just talked about. So for this first plot, what kind of plot is this? Take a minute and think about it and answer these 4 questions. This first plot is a stacked box plot, or we might just call these side-by-side box plots. The explanatory variable is this categorical variable of whether someone is using a cell phone or not. So this is our explanatory variable. It's unusual, or it's different, to see the explanatory variable on the vertical axis. And it is, as I said, categorical. The response variable is response time, and it is quantitative. When we have a box plot, we know that the response must be quantitative because box plots can only be used with quantitative response variables. We have an outlier here. Box plots don't always indicate outliers. Sometimes they'll just draw a really long tail or a really long whisker. We see here between these 2 levels of the categorical variable, so for those who are using cell phones, we see that it looks like it is right skewed. There is a long right tail here. However, for the control group, for those who did not use cell phones, it looks roughly symmetric. One thing we cannot tell with a box plot is the modality. So we do not know if this is unimodal, bimodal, or amodal. Well, it can't be amodal if it's skewed. The center for the cell phone group is at about 550 milliseconds. The center for the control group is lower at about 525 milliseconds. So for the cell phone users, they had a longer response time, typically. The spread for the 2 groups is about the same. The IQR for the cell phone group is about 100, and the spread for the control group is also about 100. It may be a little shorter or smaller for the cell phone group, but they're approximately the same. Now let's look at plot number 2 here. Please answer these questions. What type of plot is it? What is or are the explanatory and response variables? What kind of variables are they? And how would you describe these data? This second plot is a bar chart. For a bar chart, we must have a categorical variable. And the categorical response variable, in this case, is the education level. Again, our response is plotted along the horizontal axis, which is a little different from what we're used to. There is no explanatory variable. What is being plotted on the vertical axis is just the percent or proportion or relative frequency in each group. So this is not a variable. This is similar to what we did when we were looking at the percent of shark attacks before. There was one variable and then there was a count and a proportion of groups in each variable. If we want to describe this chart, we might say, or describe this distribution, we would say that the education attainment levels, the proportion or percent of people with at least some college is about the same as those with high school or equivalent. However, the proportion of people with no high school diploma is about half of that with high school, some college, or at least a bachelor's degree. So what we're going to do is we're going to compare the heights of the bars. Now we have plot 3. Interpret this plot. What kind of plot is it? What is or are the explanatory response variables? What kind of variables are they? And describe the distribution. In this case, we have a segmented or stacked bar chart. Just as before, if we have a stacked bar chart, that tells us we have a categorical response variable. We also have a categorical explanatory variable. So in this case, our explanatory variable is food type. And our food type, being represented as organic or conventional, must also be categorical. Our response variable then is whether the pesticide status is our response. So the status of the pesticide, which has levels of present or not present, that is our response. And because it's present or not present, that is also categorical. So the two different segments of the bar chart of each bar are the levels of our categorical response. So to interpret this plot, to describe what's going on, the distribution of pesticide status for conventional food types is very high. There is a much higher proportion of pesticides in conventional foods, this box here, than there is in organic foods, because the proportion of pesticide status in organic foods is very low. So we're still going to compare the heights of bars, it's just the relevant heights of bars. For plot 4, what kind of plot is it? What is or are the explanatory and response variables? Describe the distribution, and what kind of variables are they? This is a histogram. The response variable is the amount of sodium. It is a quantitative response. We can only do histograms with quantitative response variables. Just as with bar charts, the vertical axis being frequency or proportion or percentage, that is not a variable. It's just describing how many observations fall in a given bin. So this is a univariate plot. What we can see, if we were to draw an approximate curve over here, is that this is roughly unimodal and symmetric. The center is approximately at 200 milligrams. And to assess the spread, I'm going to use the range, and the range is at about 360 milligrams. With one last plot, we're going to do the same thing. What kind of plot is this? What is or are the variables? What is or are the explanatory and response variables? What kind of variables are they? And describe the plot. This is a scatter plot, or we might say a scattergram. The explanatory variable is the number of votes for Ross Perot. It is quantitative. The response variable is the number of votes for Pat Buchanan. It is also quantitative. We can only do scatter plots when we have a quantitative response and a quantitative explanatory variable. If we had a categorical explanatory variable, everything would look really clumped together. We would have something like this, and then something like this, and something like this, and it really wouldn't make much sense. We do have evidence of an outlier or an unusual observation up here. So for this group where there were 30,000 votes, or this county where there were 30,000 votes for Perot, there were also 3,500 votes for Pat Buchanan, which is outside the usual trend. Most of the time when there were a lot of votes for Perot, there were not many votes for Buchanan. So to describe this, we would say there is a linear association. It is in the positive direction, because I could draw a line. It has a positive slope. As the number of votes for Perot increases, the number of votes for Pat Buchanan also tends to increase. There is one abnormality, one unusual observation. And I'm going to say that this is a fairly strong association. And we're going to talk more about this next week. But what I mean is that all of the points fairly close to my imaginary line that I drew. I don't have a lot of spread, so all my points are very closely clustered around that line.